Okay, we're good to go.
Yeah. Yeah.
Do you want to share your screen or should I?
I don't know, it might mess up the network. So if it's okay, you can share on my end. It might mess up the network on my end.
Okay. You can see my screen, right?
Yeah, I thought you were going to continue.
Oh, okay.
Or should I take over?
Yeah, build external DSLs for flexible syntax. So in the previous chapter, we were talking about internal DSLs. This chapter is about external DSLs, and an external DSL is one where you no longer rely on Ruby or the Ruby parser. Uh, you are you are creating your own language with its own syntax and its own rules. And because you're creating your own language with its syntax, you are going to need to create a parser to parse that language. Okay, so to see why you might build an external tool instead of taking advantage of all the wonders of Ruby, we previously defined this as being the syntax that we were going to use to define the rules for dealing with XML files, right? But now the our utility has found a different audience, maybe a more lay audience where first you were dealing with uh, only programmers, and now it's now other people, other users who are less technical want to be able to use this same functionality. They've requested that the syntax be simplified to these commands, print and then document slash author, or delete, document published, or replace, document author with Tolkien. Um, these are not going to be valid Ruby syntax. And because they're not a valid Ruby syntax, we're going to have to create our own. Um, well, basically, this is going to be our own language, and we're going to need to create a parser for that language. Okay, so we're going to change this class, Easy Ripper, to now be able to parse the program. Okay, so we're gonna open up that command file with the .ripper extension, and we're gonna parse each line. So each statement will be on its own line, and we're gonna parse each statement and basically into the different commands that we have. So this parse statement will basically take the statement, strip it into different tokens, and we're going to look at the first um, string of that token. So this is what's going to happen when we find uh, the word print. Basically going to put put that text here. We're going to delete el.remove. Great. Replace. We're going to take that text and replace it with the second token that we find. Great. And then we're going to print the document. So this is going to work. If we get some other keyword, we're just going to raise an exception and say we don't know what to do with it. So these
So
are the commands that we,
Nelson,
yeah,
I have a question regarding this piece of code.
yeah.
When you talk about, because this is actually the chapter that confused me the most. When you refer to tokens or to a token, what exactly are you referring to, and why do you have to keep track of the tokens? Like we'll say in the examples that come after the variations of this code, you keep on having to keep track of the number of tokens. So what does that mean? Or
Oh,
what's the use
okay.
of that?
So this is where we define tokens, right? So it's
Yeah.
just going to be statement.strip.split. Okay, so we're gonna open up IRB. Okay, this is a statement that we will break into tokens. So dot split, we'll break it into different tokens. And now, instead of a simple string, we have our individual tokens. And in this case, our individual tokens are just these words that we put into this statement. So if we call dot first on these token, oh, actually, maybe we should assign this to a variable. So now we have tokens. Tokens dot first is going to be this. Okay, so what if our token was print document author? Copy dot split tokens. Okay, so tokens dot first is going to be print, and then tokens at some other index, let's say index one, is going to be document author. So in this code, we split up the code into the different tokens, and then we basically say, okay, what is the first token? When the first token is print, this is what we're going to do. When the first token is delete, this is what we're going to do. And so we're going to handle all of those different commands that we said we wanted to handle: delete, replace, print, and those things.
Yeah, so when you pass it, when you try to access the token at index number one, that is what you pass in as the path of the file, according to what I'm understanding.
Hmm. Yeah.
Okay, okay,
So yeah, tokens one is going to be document author.
yeah,
I mean, it's the path, it's the X path that we're going to use to
yeah,
parse the XML. Yeah.
yeah,
Okay. Okay. So we're doing all these commands. Print document will tell Easy Ripper to output the modified XML. To run our little program, we simply need to feed it and the name of the XML file into Easy Ripper. So easyripper.new. So we're going to take edit, and this is an arbitrary file extension that we've defined. So it's these are the edits that we wanted. These edits live in the edit.erz file. So these are our commands. So we're gonna initialize Easy Ripper with the commands that we want. Then we're gonna call those run on this fellowship.xml file. So the Easy Ripper class just provides a fancy front end for the original XML Ripper class. That's all it's doing. So this XML Ripper class was the original class that we saw in the previous chapter. And basically, we're doing all the same things from the previous chapter, from that XML Ripper class. And now this Easy Ripper just provides a way for us to easily run those commands by uh, by basically parsing these statements for us. This is our parser. This entire class is our parser. Okay,
yeah,
so um, here's what we're doing. We're when someone gives a wrong error or a malformed command here, that for some reason they call delete without, giving the path. We're just going to check to make sure that we have the right number of tokens, right? So if we don't have the right number of tokens, we're going to raise an exception. So for each of these, we're going to check for the right number of tokens. The tokens have to be two, two. Here we're checking for three tokens because we have the command replace, we have the
Path.
yeah we have the first argument and the second argument,
Yeah.
what we
Yeah.
want to replace and what we want to replace it with, and then print document token
Yeah.
size one because it's just print. Okay. Anything else? We just say, okay, we're going to raise an exception. We don't know what to do. Okay, so within certain limits, it's also easy to add new features to Easy Ripper. We might, for example, add an uppercase command that converts the text of the element to all uppercase. So this is all the code. Whoops, what is this? Oh, okay. Yeah, it just forget about that. That was the previous video being it had finished converting the video. Okay, so uh, we might also want to add comments. Um, the hashtag will be our comment separator, and so we're gonna basically like not run any code that starts with a comment. So um, okay, great. I mean, we're just basically adding commands and adding a little bit of functionality. So this works for easy cases. What about for heavier parsing? Um, so now, let's say that we want to tackle cases where we need to handle spaces. Like Russ Olson, we have a space in between here, so we're not going to be able to get away with just parsing based on spaces because we're relying on the tokens being of length two or length three, and when we start parsing based on spaces, it's going to be one, two, three, four tokens long. So we're going to need to add quotes to delimit where our spaces or to delimit where our tokens actually start and stop. So this is going to be our first token. That's going to be our second token. Great. We have a replace which is three tokens long. So how do we implement this? Well, we're going to use regular expressions. So we're going to start this pattern. So this is the entire regular expression, and this is our print statement. So remember, our print statement before was just basically saying, okay, when it matches, just this word. Now, our print statement is going to start with the word print. It's going to include us at least, well, it's going to include at least one space, and then it's going to start with this quote tick and end with a quote tick. And these parentheses define a capture group, and this is going to be the first capture group defined by this number one. So the capture group is basically dot star question mark, which is basically anything, anything in these quote marks. Okay, so when it finds that print statement, it's going to put uh, anything in these quotes into the first capture group. So here we can use the first capture group, ripper.onPath, and we give it the capture group one, and then it puts el.text. Great. So we do basically the same thing here on our delete, where we're putting that first thing that we find in single quotes into our first capture group, and then we just use that capture group. We call el.remove on that. Then for replace, replace takes two capture groups. So we have two sets of parentheses here. This is our first set of parentheses and our second set of parentheses. So the first set of parentheses we're going to call Ripper on path, and that's going to be the path that we search the XML for. And then the second set of parentheses defines what we're replacing that text with. And so we say $1 for the first capture group, $2 for the second capture group, and that's our replace statement. Uppercase. Great. So, it's pretty simple. We have one capture group. We send the whatever's inside that capture group to these el.text.uppercase. Um, so regexes will work, but when your syntax start getting more complicated and more complex, um, you're going to have to write more complex uh, regular expressions, and worse, you're going to have to read more complex regular expressions. And uh, when you're creating these very, very complex regular expressions, you're going to make more errors and it's going to get harder, not just linearly harder, but probably exponentially harder to create and read the regular expressions. Okay, so what about jobs that exceed the limits of our regular expressions? Once they start to get too unwieldy and too difficult to create. Well, our parser can be created with this utility called treetop. Um, treetop. Okay, so this utility basically lets us define a grammar into an individual file. So you create a grammar rules, and we're gonna call it an easy ripper statement. And these are the kinds of statements that we have. We have a comment, we have a delete statement, replace statement, and a print statement. And here we have a rule. The rule is that we have a comment. The comment is going to start with a uh, hashtag or pound sign or octothorpe. And then we're going to just uh, comment out anything after that. We have this delete statement, which starts with the word delete, has a space, has a quoted argument, and then has a space. We have another rule called the replace statement, which starts out with the exact text of replace, has a space, quoted argument, space, quoted argument, space. Um, Print statement has starts out with the word filter, space, quoted argument, space. Okay, so now that we've defined our rules, uh, this utility will need to be compiled. This is how you compile it. TT easy ripper statement.tt. It will create a easy ripper statement.rb file, and that RB file will be our brand new and shiny parser. Um, I don't know anything about this treetop utility. I've never used it. I don't know if it's still up to date. Actually, maybe we should check that. Top gem treetop. 15 years ago, 12 years ago. Okay, so it looks like the last time it's okay. This repository is unmaintained in favor of this one 2 months ago. Okay. Okay, so it still exists and it's maintained by somebody else. But luckily, it's still around and last updated as of 2 months ago. So it seems like someone is still taking care of this. So yeah, okay, we can still use this treetop utility. So we're going to require the treetop utility. We're going to require our Easy Ripper statement, and then we're going to basically create the statement. Replace document author Russ Olson. We're going to create this parser, Easy Ripper statement parser.new, and um, this is our parsed tree. So run this code and you will end up with your statement parsed out into a tree structure that you can programmatically descend and interpret. Great. So basically, to you, I would start out by reading the tutorial here and how it's used, the grammars, the syntax, all that stuff in order to get started with Treetop. And it looks like a great little utility to be able to create your own DSLs, uh, external DSLs. To no one's great surprise, the advantages and disadvantages of external DSLs are a mirror image to those of internal DSLs. So with internal DSLs, you get all the great features of Ruby and the syntax, comments. You don't need to define comments. You don't need to define loops or if statements or any of that. With external DSLs, you need to work for it. Um, this is an example of Haml. Haml is a very, very terse language. It lets you write HTML using this very terse syntax. So you start with an opening or an HTML tag, a body tag, a main. I think this is going to be create a div with the class of main. The content today is, and then here's some uh, probably Ruby code, time.new. So this equal sign, I think, starts a Ruby statement and time.new. So I haven't used Haml, but it's basically like, guess what? I just read it. I just read Haml. That's the power of um, a domain specific, or yeah, a domain specific language. So there it is. So all of this convenient terseness does come at a price. So Haml relies on this code to do its parsing. Um, yeah, this code doesn't. It looks like it requires a lot more thought. This was. I didn't have to think about this at all. The parsing of that requires a lot more thought. And it goes on and on and on. So it's a lot more complicated to parse out that language. Uh, wow, clearly writing the Haml parser took some real effort, which seems worth it when the result is Haml. Great. Um, okay, in the wild, uh, for languages known for its internal DSLs, there are rather surprising number of Ruby-based external DSLs around. Um, So Haml is one of those. ERB for templating, HTML templates as well. Um, this is just an example of how ERB defines the regular expression to split up the um, how it finds ERB statements in the document. It also talks about Cucumber and how Cucumber is great because you can define statements in Cucumber like this. The feature is the count of words in a document. And basically, this is human readable language that is going to define how we test how we test our code. Um, this is more Cucumber, how Cucumber works, and that's basically it. The it explored the power of external DSLs, but also external DSLs are no cakewalk to set up because you're gonna need a parser and you're basically creating your own language. So good luck. Okay.
Yeah, I think that's it for these two chapters.
Yeah, that was very interesting.
So two more chapters and we are done with the book, I think.
Yeah.
29 and then 30.
Yeah, packaging your programs as gems and know your Ruby implementation. So,
Yeah.
yeah, I've never created a gem. That'll be interesting. Um, and then, oh, we have chapter 31.
You think we should do three of those at once? Or we should
Oh,
do two and
that's
then
one
the last
page
one?
long. Yeah, we'll do that one too.
Okay. So I think that's a next Friday thing.
Hmm. Yeah.
Yeah. Okay.